Example 3 says, if y is equal to 1 over the square root of 2x plus 5, then find dy dx. Now, prior to this section, we could find the derivative by using the quotient rule, since we have a function divided by another function. However, I think using the chain rule in this instance will be a little bit simpler than using the quotient rule. So before we start using the chain rule, I'm going to rewrite our function to be 2x plus 5 to the power of negative 1/2. Now, we've seen problems similar to this, but notice that we have a little bit more of a complicated function inside. And so when we take the derivative, dy dx, what we need to do is, you could think of this function as u. And so if this was u to the negative 1/2 power, then our derivative would be negative 1/2 u to the negative 3/2 power times du dx. And so off to the side here, if u equals 2x plus 5, then the derivative of that with respect to x is going to equal 2. So then I'm going to do some substitutions. So I'll replace u back in. So we have negative 1/2. Our u was 2x plus 5 to the power of negative 3/2 times du dx, which we calculated over here to be 2. Let's do some more simplification. So I'm going to multiply negative 1/2 times 2, which will just be negative 1. And then I'm going to rewrite the rest of that as the square root of 2x plus 5 cubed, like that. So I just didn't want to use a fractional exponent or negative exponent notation, so I just rewrote it like this, but that and the above thing are the same thing. Example 4 says differentiate f of x equals the quantity 5x to the 6th power plus 7x all raised to the 10th power. So before we start to differentiate that, I'm going to determine my u, which is my inner function. So that's 5x to the 6th power plus 7x. And then ahead of time, I'll just calculate du dx, or the derivative of that. So that's going to be 30x to the 5th power plus 7. So f prime of x will equal 10 u to the 9th power. So I've used the power rule there, and then I need to multiply this by du dx. So that's going to equal 10 times u. I'll substitute u back in. Okay, and we can just leave it like that. If you want, you could distribute the 10 into these two terms, but I'm just going to leave it as is. So this is our derivative using the chain rule for this problem. All right, so this is a little bit more complicated. Example 5 wants us to differentiate the function f of x equals 2 times 3x plus 1 to the 4th power times 5x minus 3 to the 2nd power. And the reason that it's a little bit more complicated is because we are going to need to use product rule and chain rule. All right, so let's get started. So we have f prime of x is equal to, I'm going to leave the constant on the outside, and then we want the first function times the derivative of the second. So I'm going to bring down the 2 times 5x minus 3, and the 5x minus 3 is the inner function, and I need to take the derivative of that and multiply it. So the derivative of 5x minus 3 is 5, plus, so we did first times the derivative of the second, plus the second times the derivative of the first. So I'm going to bring down the 4, and I have 3x plus 1 to the third power, and now I need to multiply by the derivative of the inner function, or the u function. So 3x plus 1, if I take the derivative of that, that gives me 3, and then I can close off the parentheses. So just if I write this out, maybe this will be helpful. So it's the first function times the derivative of the second function, plus the second function times the derivative of the first function. And when I'm taking the derivative here and here, this is where I ended up using chain rule by taking the derivative of the inner function. So just keep that in mind. And then maybe we can do some simplification here so our function's not so ugly. So we have 2 times 10, so I multiplied the 2 and the 5. And then here I can multiply the 4 and the 3, so I have 12 times and if you want, maybe you can distribute in the 2, but other than that, leaving it as is okay. So I'm going ahead and I'm distributing the 2 in from the outside of the brackets. And everything else is quite long. So we could just leave our derivative function like that.